Hello, everyone, and welcome back to our meetings about the implementation of the Thorne calculus. And let me share my screen, or actually the Isabelle window, Isabelle IDE. So here we go. So as you are probably aware of, we are still in this first part, this part on the transition system framework. So as I pointed out, this transition system framework is independent from the Thorne calculus, and that it works for the whole class of calculi. And actually everything apart from this up to context even works for things that are not process calculi, just graphs, actually labeled graphs that are so-called labeled transition systems and describe how systems behave. So, and we are still here in the subsection on up to methods. And today I want to show you finally why these respectful functions that we have had a look at, why they are sound regarding this up to technique. So why is it possible to do up to proofs and have them being correct if we base the up to proofs on respectful functions? And I mean, you have seen these pictures many times, but let me start from here. So the point was that we have defined by similarity our notion of equivalence that we want to use as so it's basically the largest bisimulation relation. So I have this co-inductive definition, which boils down to the same thing. And there is this notion of bisimulation relation. And it says something is a bisimulation relation, some k, if this k bilaterally progresses to itself. So progression was in general that you have a k and an l. So L can be different from K. And if you make a step on one side, you have these processes here related in K, you must be able to make the step with the same action on the other side. And the resulting processes must then be in relation L. And specifically for bisimilarity, you have this fact that bisimilarity is the largest bisimulation relation where both relations are the same. So K is a bisimulation relation if it bilaterally progresses to itself. So, but as I already pointed out, just using directly this fact for proving bisimilarity of processes is often quite involved. And why is this so? Well, ideally, we want to prove that certain processes P are bisimilar to certain processes Q. For example, we want to prove the commutativity law for some parallel composition operator and some process calculus. It looks like this. So S parallel T is bisimilar T parallel S. And ideally, we would like to have our relation K only relate processes S parallel T with T parallel S, so that we only have to consider these when showing that this bisimulation game is working out. But this means that the process we get into, this P prime and Q prime, they must be again of this form. So again, parallel compositions where one is, so to say, the swapped variant of the other one. And this is not always the case, because you can make it into processes that are, or process pairs that are slightly different from that. And the general idea is you get into some pair of processes that are related by some relation f of k. So it may depend on k, but might not be quite k. So the f could, for example, realize the fact that you don't get in precisely something related by k, but you have some additional context. This is then up to context. Or that you get into something that's only bisimilar to processes that are in relation k. This would be up to bisimilarity. So the general thing is that you have some function f and it's f of k. And what we would like to do is we would like to be able to prove that k progresses to this f of k, and from that conclude that still k is subrelation of bisimilarity. So if bisimilarity is the largest bisimulation, then obviously any bisimulation is in bisimilarity. So if you have proved that our K is a bisimulation relation and P and Q, like this S parallel T and T parallel S on relation K, we have defined K so that this is the case. And we know P and Q are bisimilar. But now we want to have this slightly different statement proved, or we want to be able to prove this slightly different statement and still conclude that K is a subrelation of bisimilarity, so that we can know, okay, if K captures the pairs P and Q that we are interested in, then P and Q are bisimilar. And the statement that I have already made and that I want to show you the proof for is that if F is a so-called respectful function, then this proof technique is indeed sound. So already from K bilaterally progresses to F of K, we can conclude that that K is included in bisimilarity. So, but why should that be? Well, let us first think about this a bit, what we actually prove if we have progress from K to F of K, and how we could kind of argue that this gets us to the statement that K is included in bisimilarity. So in general, we have that K. So this is the normal bisimulation, right? K bilaterally progresses to K, and if you show this directly, then K is included in bisimilarity. But now we have this slightly modified relation, F of K. And what's the problem now? So we know, okay, given P and Q in relation K, and we make a step on either side, we can make a step on the other side with the same action alpha, and the processes P prime and Q prime we end up are now in F of K. And now we must show that if we make a step from P prime, we can simulate it by a step from Q prime, and we again get into something that's on a certain relation. And also vice versa, if we make a step from Q prime, we can make a step from P prime. But why should that be possible? Well, we have nothing directly proved for F of K on the left-hand side. We need some sort of statement that says, okay, F of K progresses to something, or something quite like this. So F of K progresses to something that would already be something. We don't want to make a string. This is what we want. Okay. However, now we say, well, this proof technique up to is not sound for every F, but we pick F to be respectful functions. So what are respectful functions? So we have seen that. And it's a kind of preservation property that we have. So function F is respectful if and only if for all relations K and L we have this property holding that if K progresses to L, then Fk also progresses to F of L. Now this uses this shortcut progression, but for now I want to just assume that it's not really shortcut progression, but it's this ordinary bilateral progression. Shortcut progression is stronger than bilateral progression, and sometimes we need that if we go to up to, not one moment, it's not stronger, it's precisely weaker, because what does it mean? Now, not the shortcut progression, but respectfulness with the shortcut progression is weaker, because it says on the left-hand side that K bilaterally progresses from L and K is included in L. This is what the shortcut progression says. And then on the right-hand side, you have also these both statements. Probably they're even incomparable, but the bottom line is why we want this shortcut progression is that in order to show that this progresses on the right-hand side with the shortcut progression, we have to in particular show that it progresses with the ordinary bilateral progression, which is part of this statement. And in order to prove that, we can now assume that K shortcut progresses to L, so not that it bilaterally progresses to L only, but also that K is included in L. And this is necessary for up to context in typical process calculi, because often we can show this Fk progress to F of L only if we also have this K included in L. And this has to do with the fact that if you have a process in some context, or there are some other stuff around in this process to form the whole process term, then, and you can make a step with this whole process, then this can originate from a step, from a transition of this encapsulated process that's in this context. But sometimes this encapsulated process does not make a step, but only the thing around makes a step. So you have to account for the case that this encapsulated process doesn't make a step at all. And then we need this inclusion, K included in L, which I showed is actually bilateral progression for no step or no activity transition system, where you can go from every state to itself. Right, so that's defined in terms of shortcut progression, just to make this whole development also applicable to up to context. If we would have the ordinary bilateral progression here, then it would work out except for up to context. And we can look at the idea of the correctness proof first by pretending this is just bilateral progression. So it makes it a bit simpler. So we have now the condition that F is respectful in this weaker sense. No, it's stronger sense, actually. So based on bilateral progression. I hope I don't confuse this weaker, stronger now here, but maybe you have to check yourself later whether I told you something wrong. But so we know now if K progresses to L bilaterally, then F of K progresses to F of L. So now let's our L be this F of K here. So if K progresses to F of K, then F of K progresses to F of K. Okay, and that's not so bad, because now we at least have a progression statement for this F of K. So we know, okay, if F progresses to F of K, we can play this by simulation game and end up with processes that are on F of K. Then we know this F of K progresses to something else. So we can play a next step in this by simulation game and say, okay, if one of these processes, P prime and Q prime, makes a step, then the other one can make a step with the same alpha or beta or whatever we have here. Then we get into some P prime prime, Q prime prime, and these are again in a certain known relation. It's just now F of K. So, and now, do we have this progression statement for F of K? Well, actually, yes. And why is this? Well, again, because of respectfulness. Because given that we have this statement, we can apply this respectfulness property, this preservation property. So if F of K progresses to this, then F of K progresses to F of the thing above. And we have this. Now, of course, this can go on and go on. And it shows us that we can play this by simulation game as long as we want, so infinitely long, in essence. And this means that actually P and Q are bisimilar. That's the statement they have to fulfill, that we can play this by simulation game as long as we want. So it's a kind of an informal or semi-formal proof of the fact that if K progresses to F of K and F is respectful, then K is included in bisimilarity. So any P and Q that is in K is bisimilar. So they are bisimilar. Okay. Are there any questions up to this point? Okay, then let's go on. So I could now go forward and take the definition of the bisimilarity relation which is a co-inductive definition. Then I have a co-induction principle generated by Isabelle, and I could do a co-inductive proof. I think I could do a co-inductive proof that basically captures what I have described here, that I can play this bi-simulation game as long as I want. This is not how it's done in the code. So the way it's done in the code is that we reduce this problem, this correctness problem, basically to this thing on top. So we had this idea, okay, bisimilarity is the largest bisimulation relation. So if you can come up with some relation K that is a bisimulation relation, then we know it's included in bisimilarity. And how the proof works for the correctness of this up to is as follows. We create a relation, we derive a relation from this K, such that the K is included in this relation. And then we prove that this other relation is an ordinary bisimulation relation. So the K is a bisimulation relation up to F. We derive some that somehow uses this F, of course. It is then an ordinary bisimulation relation. And then we know that this is in bisimilarity, because any bisimulation relation is. And since K is in this relation, then by transitivity of inclusion, we get that K is in the bisimilarity relation. So, and how could this relation look like? So in this proof approach here, I always had different relations, right? I went from K to F of K, then from F of K to F of K, and then from F of K to F of F K. But now we need to find a single relation that is a bisimulation relation. Was there some question?
No, I just wanted to say, yes.
Yeah, we want to say, we want to find some sort of master relation that includes them all. The idea is to form the union of K and F of K and F of K and so on and so forth. This was also what I would have thought should work. It's not quite like that. What I think it does not work like this, so that you have the union of this F to the power of n of K, so the repeated application of F. This does not work because I think at some point you would then need a statement that this F is monotonic. And I think all our Fs that we use in practice are monotonic, and all the Fs that we are dealing with in this framework are monotonic, but it's not necessary to require that. But actually we do require that if we go to the shortcut, right?
In the respectfulness, I think.
Yes, so if you go to the shortcut thing,
yeah, exactly.
then in fact we do require it. So maybe that's a good idea. So maybe we could even use the F to the power of n. Maybe I can simplify the proof. I should look into it. But I had several attempts, and in the end I settled with something that was very close to this paper by San Giorgi, because I couldn't make it work otherwise. But maybe I should I should reconsider that. Maybe the proof becomes simpler this way. Yes.
Yeah, I mean, this respectfulness kind of restricts this condition to only where the function is monotonic, right?
Yeah, for sure. So we have this K progress to L, and K is included in L, and likewise for the right-hand side. So from this conjunction, we get this conjunction on the right-hand side, and this in particular means no. One moment. No. It does not say it's monotonic. It does not say that. It says if K is included in L and K bilaterally progresses to L, then we have the inclusion on the right-hand side. So we may use this condition.
It's inequality preserving, not monotonic. What
it preserves is the shortcut progression. And the shortcut progression is the conjunction, or the meet in the lattice, right, of inclusion and the ordinary bilateral progression. So the thing is that on the right-hand side, we have the conjunction of k progresses to L and k is included in L. And we may use both to show that fk is included in fl. I think typically you are not able to make use of this bilateral progression on the left, but in general you can. So, and therefore I think you don't get the guarantee that's monotonic, except you can really prove that you absolutely can't make use of it ever, but I wonder whether this is the case. So it's an important thing to know. It's different from saying, okay, k included in L implies fk included in FL, and k bilaterally progresses to L implies fk bilaterally progresses to f of L. This, what I just said, is a weaker statement, because then it means for the inclusion on the right-hand side, you can only use inclusion on the left-hand side, and for proving the bilateral progression on the right-hand side, you can only use the bilateral progression on the left-hand side. But in both cases, you can use both. So it's slightly, it is a weaker property. Exactly, it's a weaker property, something that's in general easier to prove. And it's, at least for, we go to right-hand side for the bilateral progression, this is exactly what we need. And this is exactly why we introduced this inclusion thing at all, or the main reason at least for that, because in this up to context, we can only show that fk bilaterally progresses to f of L if we know the bilateral progression and the inclusion on the left-hand side. For the inclusion on the right-hand side, we might not need both on the left-hand side. Inclusion might be enough, but for the bilateral progression here on the right-hand side, we sometimes need both on the left-hand side. Okay, so we don't assume that this f is monotonic, although I think it's in our use case, it always is. But it's not necessary. It would be necessary if we would do what Andre, I think, suggested. We just take the union over the f to the power of n. But we do something different. We first define something that I call the extension of f. That's again a function on relations, and the extension of f applied to some k is defined to be k union f of k. So it contains both, and it's this extension of f that we iterate arbitrarily many times. So what's the idea behind that? We say, okay, let me copy this. Okay, if k progresses to f of k, then it certainly also progresses to this thing here, which is this extension of f applied to k. Because it means if we have something in relation to k, we can play this by some relation game, and we get into something that's related by f of k, then it's even more related, so to say, by this enlarged relation. And then we, of course, now need to adapt this one to k square f of k, because now we have, so to say, weakened this statement for the right-hand side here. The user of this up to method has proved that the processes are on f of k, but now, for the sake of our correctness proofs, we say, okay, it's in this relation, slightly weaker relation. So we must prove that if it's in this relation, then it progresses to something. But the good thing is that we are now proving something for a relation that covers both the initial relation and this relation that we have here for the situation after one step. So, and well, this f of k, as we have seen here, progresses to f of k, and the k okay, a bit different. So the k progresses to this. So let's forget this about this on the right-hand side. The k progresses to k union f of k. So this k on the left-hand side here progresses to f union f of k. And this fk on the right-hand side, what does this progress to? Well, the k progresses to that. And because of respectfulness, this preservation property, we know the f of k progresses to f of that. Right? And now, if we have a union here, and these things individually progress to something, then this union definitely progresses to the union. Because if something is related by this union, it's related by k or by f of k. If it's related by k, it progresses to this. It's related by f of k, progresses to that. And so definitely, if you play this bisimulation game, you end up in something that is in this union relation because it's in either of the single individual relations. So, and now we can simplify this a bit. This on the left-hand side, this is just this extension of f applied to k. And this here is what? So this is extension of f of k. And this as well. I'm unlucky today. So it's extension fk union with f of extension f of k. But you see again this pattern. We have a relation. And then we have f applied to this relation. This is how the extension was defined. So this whole thing is extension of f applied to extension of f of k. So, and then, okay, we would also know, likewise, that extension of f of k is blah, 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 with 3 extensions of f, and then we take this as our relation. I'm just wondering why we are doing that, why the f iterated is not enough, and maybe it even has to do with the fact that we use the shortcut progression. Because if we would not use the shortcut progression, but the bilateral progression, then maybe we don't need this extension thing. Exactly. Then actually, Andre's suggestion is correct, I think. We just take the union of f to the power of n applied to k for any n. So this one here, union over all n of f to the power of n. This is this, which ends up as a superscript later. Actually, I can write it nicely. It's not legal Isabelle syntax. It's a single exponent, single superscript notation, but it looks better here. It's just comment anyhow. I think that should even work if you don't insist on using the shortcut progression. And why does it work? Well, we have proved k progresses to f of k. This is what the user of the up-to method proves. And then this implies that f of k here is progresses to f of k, and that f of k progresses to f of k, and so on. So every f to power of n applied to k progresses to f to the power of n plus 1 applied to k. And this means that the union progresses to itself, because whenever we have something that's in this union relation, then it must be in f to the power of n applied to k for some n. But then it progresses to f to the power of n plus 1 applied to k. But this is included in this union. So if this p prime q prime is in this f to the power of n plus 1 k, then it's also in this union. And as a result, this union progresses to itself, so it is a bi-simulation relation. So if you define respectfulness just in terms of bilateral progression without this shortcut thingy, with this inclusion, then this relation should do the trick. Are there questions or comments about that? Okay, so now, why do we want this extension where we not just apply this function f over and over again, but always include what we had previously, right? We apply the f to our previous relation, which is k here, but then form the union with the k. This is because of the shortcut progression. And what's the problem? You could say, okay, if this is not bilateral progression, but shortcut progression that we use here, then the whole argument works the same way, and we get the union of f to the power of n and not some extension of f. Of course, we get then the fact that this is a bisimulation relation with respect to this shortcut thing, but the shortcut thing is, yeah, maybe this is already a problem, but there's also another problem, because what the user proves is that k bilaterally progresses to f of k. The up to method proof obligation should not include the requirement to show that k is included in f of k. And actually, in most cases, or many cases, this is not the case. Yeah, this is included. So if f is the function f that describes this up to bisimilarity proof method, then we have this inclusion, because up to bisimilarity looks as follows. So this, yeah, okay, if f is up to bisimilarity, then f of k would be bisimilarity composed with k composed with bisimilarity, like this. And since bisimilarity is a reflexive relation, therefore we have this phenomenon that k is included in f of k, because this could just be, includes the identity on the left and on the right. However, with up to context, this is not the case, because if up to context, then f of k relates processes p prime and q prime if and only if the following. So fk relates p prime and q prime. What does this mean? There exists st and u such that p prime equals st and q prime equals su, and k relates t and u. These p prime and q prime, they are of this structure. This is up to parallel context, and there are also other up to contexts. We have a common context S, and on the right you have t and u, and they must be related by k. And we see that this their k is not included in f of k, because these processes that the f of k relates, they are larger. They are larger terms. They have this additional s here, and it's not clear that these are in the original relation k. They might be, depending on the k, but in general, they are not. So the user only proves that k bilaterally progresses to f. This ordinary bilateral progression. But for making this argument, we would need the fact that k shortcut progresses to f of k. Only then we could make this argument that finally enables us to consider this relation union n f to the power of n k, where we just iterate the f. But instead of doing that, we iterate this extension of f. And then things work out. So let us try to find out why they work out. So these are really these things that you can also forget again. So I'm curious whether I'm able to come up with the correct argument, because it's really there are really details that matter here. Otherwise, the proof won't work out. So what do we have? The user. Now this argument comes here. The user proved that k bilaterally progresses to f of k. And from this, the generic framework can conclude that k progresses to this union. Because the union is more permissive, we are more permissive in regarding what p prime, q prime pairs we can have. So basically definitely the ones that we got here, that on relation f of k, they work out also with this larger relation. So, and this means that k bilaterally progresses to extension. I agree that the lambda is more important than a left angle bracket in something that has to do with functional programming. So I am not actually objecting to that. So from k progresses to f of k, we can kind of trivially conclude that k progresses to the extension of f to k. So what now? So what we want to get to is that we don't take this union, but this union here. Oh my. Okay. So now we need to find some statement regarding this extension f applied to k. What does this progress to? So we know the k progresses to this. This is what I said before. And the f has this preservation property with regarding to this bilateral progression. So f of k progresses to f of this, because k progresses to this. Okay? So this whole thing progresses to that. And then we have this. This should be correct, right? So what we basically have done here, we have derived that from the respectfulness that, yes, from the respectfulness that refers, for the respectfulness of f, we have the property that f, the extension of f, is also respectful. Maybe write this explicitly. So if f is respectful, it means that for all k and l, so this was just a special application of this general principle with this k, f, k, blah, 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 but it works for k, arbitrary k and l. No. How do I get this arrow? I used to know that. There's definitely one way to get it, to copy it. So,
quick arrow.
pardon?
I think it is called quick arrow.
No, this is the one that has more back and forth moves. This one that is Namstech, but the one that is in LaTeX Sim or so, that's this one. Leads to. This one.
I see, okay.
Okay. And what would be respectful for this, no, like that. Of course, would be like that. Now we can expand that. So this is just K union Fk. That's L union f of L. And now it's maybe clear why this is. Because if you have something related by that on such a left-hand side, that's related by K or by f of K. If it's related by f of K, then from this, we can conclude Fk leads to f of L, or f shortcut progresses to f of L. Then we know, okay, this Fk shortcut progresses to f of L. So if we have some pair that is related by f of K, and we can play this by simulation game, we have something that's related by f of L. So it's definitely related by this larger relation here. But if the original thing is just related by K, and we have assumed K shortcut progresses to L, well, then shortcut progresses to L, and so also shortcut progresses to this one. So the idea is we need the shortcut progression for up to context to count as respectful. So we must prove everything for shortcut progression, not just for the ordinary bilateral progression. But what the user is supposed to do is only to show that K bilaterally progresses to f of K, not that K shortcut progresses to f of K. And this is not even true in general. So we cannot work with this union over all f to the power of nk, but instead we take this extension from f that includes this argument here, in this case is K. But we have this lemma that from the respectfulness of f, we can conclude the respectfulness of the extension of f. If the user has proved this, from this, the general framework derives that we have this, that also progresses to extension of f of k. And now the extension of f is respectful. So we know k progresses to extension fk, and since its extension of f is respectful, extension of fk progresses to extension of f extension of fk, so on and so forth. So we can capture all these statements or make use of all of them and show that if we start with the union of all these repeated applications of the extension of f, here, then this union bilaterally progresses to itself. And therefore, it's a bisimulation relation. And therefore, it's included in bisimilarity. But since the k is included in this relation, because if you set n to 0, then you have it, k is included in bisimilarity. That's basically the proof. So, and so we saw that it's kind of important that we include this previous case, or this previous relation at every step, which is what this extension of f is doing, so that we have processes of this form. So we have k, and then we have f of k, but then we take both together and apply f to them, but also take them without the f into this relation, and then we have something that looks like this. And then, of course, repeat it. And this is just a repeated application of extension of f. Are there any questions about all that? So if not, I'd like to now go to the actual formal proof. So last time we saw the beginning of this subsection on up to methods. So I defined what the simulation by simulation up to is. This is exactly this k progresses to f of k unilaterally, bilaterally. And now for the soundness. So I was wrong. It's not called extension, it's called expansion. Okay, then I mean, it's similar. It's just 2 letters different. So the expansion of a function f of this type, so again, a function of this type, and it uses this syntax. So the parentheses here, they are just for pretty printing, I think it was, yeah. So they are not part of the syntax. The syntax are these angle brackets, and the underscore marks the argument, so you can write it as I did before. So I write this in this point-free style again. So the expansion of f is the identity joined with the f. So if you apply the expansion of f to process p to relation k, then it's k union f of k, and this is what we saw previously all the time. So, and then I have this lemma expansion is respectful. So these names are maybe always a bit misleading, but at least I'm consistent with this. What I mean is that the expansion of some function is respectful if this function already is respectful. So it's a preservation property. But I wanted to take care that these names don't get too long. They are actually longer already than the standard library names, which very much use abbreviations. So I'm already a bit elaborate here. So assuming that f is respectful, this lemma shows that the expansion of f is respectful. And so how do we prove that? So first, we unfold using the expansion def. So unfolding just does rewriting by equation. So it's basically what the simplifier does. It's just that the simplifier is a bit more automatic, so it considers standard rewriting rules that are registered to be taken by default, and it does a bit more. For example, it can resolve trivial statements in the end, like x equals x. So unfolding is really just application of equations and nothing else. So the expansion definition is this one here. So expansion, if we define something called expansion, then this automatically defines a fact called expansion def, which is precisely the defining equation. So, and if we use this unfolding, then we get exactly this here. So we have unfolded the definition of this expansion. And then we use certain lemmas, namely that the identity is respectful, and that union is respectful, so that union preserves respectfulness. This is something we have proved already. And the assumptions, there is only one assumption. So if you say assumes, then we get this assumes identifier, which is the list of assumptions. Fact list, it's just one fact. It's respectful f. So we have all this here, and from this we need to derive this, and this can be done by the iProver, which is an automated proof method that does intuitionistic reasoning. So typically in such case, I would use BLAST, which is a classical logic reasoner, but here BLAST doesn't work. BLAST often also gets stuck because it gets it's searched into branches where it cannot get out of anymore, or where it just takes too long. So why is this? Well, it's pretty simple actually. So identity is respectful. So now this f here becomes identity, and this g here becomes our f. Right? So this in particular means if identity is respectful, which it is, and f is respectful, which it is in our case, because we have this assumption, then identity union f is respectful. I'm wondering why I need this iProver, because this is really just trivial, right? You just apply implications, and maybe it would work by the simplifier, but the simplifier maybe applies rules it shouldn't apply. So I say only nothing, and then actually it works. But iProver looks nice. It looks intelligent. It's rarely used, I think. So it's really just trivial logical reasoning. So it's the iProver is much stronger than just being able to solve that. But now we get to our kind of key lemma, which is not the final lemma, but which is basically about the part that I spent most time on in my explanation. So it says, if respectful f and k is a bisimulation relation up to f. So f is respectful, and we have this bisimulation game working, right? If you have something related in k, we make a step on one side, we can make a step on the other side, and end up in something related by f of k. This is what the user of up to methods proves in order to show bisimilarity, and then the user applies this up to principle. So this is what the user feeds to us, that k is a bisimulation relation up to f. That's what this diagram refers to. So f is respectful, so it should be eligible for up to methods. This is what we want to prove here. And now we have a concrete k, which is a bisimulation relation up to f. Then we show that precisely this union of expansion of f to the power of n applied to k is a bisimulation relation, which is what we had below here, that this union bilaterally progresses to itself. It's a bisimulation relation, and then in the later step we can say, okay, if it's a bisimulation relation, then it's included in bisimilarity and so on. So, and that's basically, I hope this proof is basically what I showed you. Why does it use induction? Of course it uses induction. This is just the first thing it needs to do. This is this thing here that we said, okay, k bilaterally progresses to expansion fk, and then we apply this respectfulness of the expansion, which follows from the respectfulness of f, and get to this. And of course, for the next step, we have to apply it again, so that we get expansion of f applied twice to k is expansion of f applied thrice to k, and so on and so forth. And this we prove by induction, of course. So it really is basically what I have explained. So we state first, so this is our proof, and it consists of several steps. So we first say we have this, blah, 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 and then we have the proof QED block. So this whole thing here is the proof for this statement here. And then we have a next statement, and the then says that we use the previous statement. And then we have, again, then have. So this statement is derived from the previous statement. And then we show the thesis. The thesis is what we ultimately want to prove. And this then says, again, that we use the previous established fact or proven fact. And the fact that we have show instead of have means that we not just prove that this thesis is true, but we claim that this is actually something that we wanted to prove. So something that is a proof goal. And in fact, it is. And the show says, okay, I need a proof for what I state here. This is what we provide here, this by sim. But then after it has established that, show has the additional feature that it looks, is this indeed one of our goals? And if no, then this is an error. And if yes, then it discharges this sub-goal here. So the whole thing, this by sim, blah, 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 is proved by this proof QED block. And this has these several steps. And either you have this by and a proof method, which is something automatic, so to say. Or you have, again, a proof QED block, where you have, again, such statements here with show and so on. And there you have a by, blah, blah, blah. And you could, again, have a proof QED block here. So you can have an arbitrary nesting. So by just applies a single proof method, and it must be able to to prove this goal completely. And if you have proof, then you somehow prove it manually. But at the leaves, so to say, you need by and just invoke some proof method. There are also more shortcuts for very trivial use of by, but that's not a topic for now. So what is our first statement? So again, f is respectful. The user has submitted proof that k is a bisimulation up to f. And we want to prove that this union, where we use the expansion of f here, is just a bisimulation relation, not up to f or whatever, but just something that progresses to itself, so that we can then go on and say it's, by what we already know, included in the bisimilarity relation. So we first say, okay, expansion of f to the power of n applied to k, shortcut progresses to expansion of f to the power of successor of n applied to k. For n, and this is again this outer syntax phrase for universal quantification. So again, the idea is that we can write our proofs in a kind of a bit more prose style, which ordinary mathematicians would do. So we don't need, on the outside of our statement, we don't need quantifiers for all n dot blah blah blah, but we can use this more prose thing. So we have this for any n. This is what it means. And if we have established this and our proof is complete, then we see Isabelle has translated it in something like this, where the n is now a schematic variable, which is basically an implicitly universally quantified variable. So it would be, we would have the same statement if you would have explicitly written for all n, blah, blah, blah. But if we phrase it like this, then we also have the advantage, I mentioned this already, as opposed to using the quantifier, that the n is already fixed. If you would use for all n, blah, 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 then in our proof, we would first have to say, okay, let's consider some arbitrary but fixed n, and then we go on so that we can refer to this n, because otherwise the n is just local to this statement that we want to prove. And universally quantified statements, you typically prove that you just say, okay, first fix these universally quantified variables. So I say, assume there is some n, and without giving any conditions what it should be, some random n of the right type, and then we can refer to n. But if we phrase our goal in this more prose style, then this n is already fixed. This is already also an advantage. So it's not some local variable that appears under a universal quantifier here, but it's something that appears on the outside. So we can refer to it here in this part, for example. So we want to prove that f to the power, this expansion f to the power of n, blah, 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 progresses to this with successor of n. And this proof is by induction. Induction is also a proof method. And we can use a proof method after this word proof. Here we have just used a hyphen, which basically means don't use any proof method initially. But here we want to use something initially, this induction proof method. And this induction proof method takes this goal and says, okay, induction should be over n, and then it generates two sub-goals that correspond to the two cases that we can have for the n, namely 0 or successor of something. And these are, you see below here, these are the goals that it has created. So this is just the actual goal with n set to 0. And this here on the right-hand side is the same thing we want to prove, but with n replaced by successor of n. That's the successor case. However, it's an induction. It's not just case distinction. So in order to prove that, we are permitted to assume that we have established this fact for n already. So this thing for sub n follows from this thing for n. And this is something we have to prove for all n. So independently of the n, given that for this n, we must show that it holds for the successor of n. So these are our two goals. And if you have two goals, then we can prove this by a proof QD block with the next in between. So the next separates the two sub-proofs, so to say. And now we say case 0 and case successor. So the cases, the goals for these different cases have already been generated by this induction here. This case just does some technical fiddling. In particular, it's important for this successor case, because this is a logical statement with a universal quantifier and with a premise here, so it has an implication. But it would be nicer if we could do again something like this, what we had with the assumes or with the for, that we only have this as our goal and have this already as established as a fact that we can explicitly refer to, like a lemma. So it's not just a part of an implication, but we only prove that. We have this as a local fact, and the n is already fixed. So we have assumed we have some arbitrary but fixed n. And this is what the case does. So the case is some convenience thing for these things that I just described. We could use this manually with words like fix and assume and so on, but the case does it for proofs by induction and by case distinction. And it's actually a bit more flexible. So you can also configure to work for other things that you have defined, other kinds of proofs. And this is what we see here. When we say, so here we have proved the zero case, we still have to prove the successor case. And after the case successor, we have this. So the n is fixed. It's now called n underscore because n is already the outer n. And so we have this fact, this premise as a fact here. And what we have to prove is just this conclusion here. And this is what we see here, this word question mark case. What this case statement here is introduced is really just the thing on the right-hand side of the implication. So we have this as a fact now. The n is fixed, it's called n underscore, and this is what we have to prove. And we can refer to that. So that's about this case thing here. So we prove by induction. First, we have case 0. And we show our case, which is just this thing, the statement for the 0. And for this, we use now the fact that k is a bias simulation up to f. So remember, if k is a bias simulation up to f, this is what the user provides, then we have this statement. And we said, from this statement, we can indeed derive this statement, namely that it's also by simulation up to expansion of f. So, and this is actually what we need. K bilaterally progresses to expansion of f applied to k. You see this here, expansion f to the power of 0 is just k. An expansion of f applied to the power of success of 0, so applied to the power of 1, is expansion of f applied to k. This is this one here. And follows very trivially from this one because k progresses to this, and then we can just extend this, and it still progresses. And we are able to, Isabelle is able to do this automatically with the right proof method. So it doesn't just work with the simplifier or the blast individually. It's just that initially the simp does something, and then the blast does something, and then it works out. So this I find out by experimenting a bit and having the idea how this simp and blast work. And then by combining this, you can often come up, if you get some intuition and experience with that, you can come up with these concise statements here. And the idea is, don't bother too much of why this works. The intention is that the proofs are readable, basically, if you drop these nice little proof method expressions. So they are just for the machine, and if you, in your mind, you drop them, then you get a basically human readable proof. This is the style that we are aiming at here. So whenever you have something solved by these automated methods, then the idea is our style is that we do this whenever the human would be able to figure this out, so to say, without any further notes. Okay, but this was the trivial case, but the other one is also not that problematic. So we want to show this for the success of n now. We know this is our induction hypothesis. We know it holds for n. And we can use that f is respectful. Why can we use it? Because we assume it here. So, and respectful f means something, but we don't unfold this definition actually, but we use this expansion is respectful, which we have proved here. So you see it here in our IDE. If you say using expansion is respectful, then we get this as an additional fact that we can use. So if f, any f, so this question mark is again, it's a schematic variable, so it means any f, all f. So if any f is respectful, then its expansion is respectful. But this means in particular that if our f is respectful, then its expansion is respectful. And then we can do this reasoning. If we have this progresses to that, and it's respectful, that means that we have this preservation property. We can add an application of expansion f here and here, and it's still the progression holds. And this means we can, we have this with this additional application of expansion of f. So it is just this to the power of n plus 1, or success of n, and here success of successor. And it's quite trivial. And the simplifier can do this. Here we actually not just use the simplifier, but we say del as a parameter, shortcut progression def and expansion def. And why is that? Because the simplifier will attempt to use these defining equations for shortcut progression and expansion automatically, because we always said when we wrote down definitions, we always said things like, oh, where is one? Sim. So we wanted them to be automatically considered, but here it's not quite what helps us. Here. Because then it just expands these definitions, and then I cannot possibly apply this lemma and reason about this, because we want to have this expansion of f stay as a black box. So we must tell the simplifier not to use these defining equations, and then everything works out. So that's this key part, kind of. So f, expansion f to the power of n, k, progresses to the same, but just with n replaced by successor of n. So, and then we have the following. So then we say something weaker. Here we say always, if we have this n here, then we can have the successor n here, and we get this progression. Now we have a progression from some k prime to l prime. And about the k prime, we just say it's in the range of this function, which means it is of the form expansion f to the power of n applied to k. And for the L, we say the same. It's just of this form, but this is a possibly different n. So here we say, okay, n on the left, sub n on the right. Now we say, okay, some n on the left, some n on the right can be different. Now, of course, this follows from this here, follows from that. And blast, the classical reasoner, can find this out. But the good thing is that if you have established this, so not caring about this successor or not, or whatever, just some n here, then from this we can conclude that the union of all these expansion f to the power of n progresses to the union of expansion f to the power of n applied to k. That's here we have k. So it progresses to itself. And this follows from this general union shortcut progression fact. Let me show you what it was. So this is what it says. For all k in some set, calligraphic k, and for there, if for all k in the set, there exists an L in this set, and such that k progresses to L, then the union progresses to the union. And we have this here. We have this for all k in this range. We can progress to some L prime in this range. And so the union progresses to the union. And from this, we can show our thesis, namely that this union is a bisimulation relation. Well, this follows from the definition of bisimulation relation. So the simplifier can do it. We could write it more explicitly, just basically unfolding the definition. No, and actually it's not it's not so trivial, because this is a shortcut progression, right? So this says that this shortcut bilaterally progresses to itself, and it's also included in itself. And we drop also this inclusion because it's trivial and we don't need it for this being a bisimulation relation. And then we have this key lemma. We've established that if we have been given a relation K that's bisimulation up to F, and F is respectful, then this union over all these expansion F to the power of N is a bisimulation relation. Are there any questions? Okay, then let's get to our final theorem. There's a bit more stuff here, but we can do this next time, I think. The real bulk is what we have basically done. And this is just the bit that is missing for that. So up to is sound. This is this key theorem. Up to methods are sound for respectful functions. So assuming we have a respectful function f, and k is a bisimilarity up to f. This is what the user gives us. So the user picks some function f, and as I said, so this function f is composed from trivial respectful functions by some operators, and then we have this little automated prover that can then uses this preservation lemmas to show that f is respectful. So this is an easy thing. The user composes a custom function f that's respectful for, this is good for the particular proof, particular bisimilarity proof, and then also supplies this statement that k is bisimulation relation up to f. This is the harder part. Then this up to sound shows us that k is included in bisimilarity. So everything that's related in k is consequently then bisimilar. So, okay, what do we do? From the assumptions, so this is what the assumptions are here, what we have listed here. So we use these two facts. From this we have that this union is a bisimulation relation. Well, and this is exactly what we had here, right? Same assumptions and blah. So this follows by the fact bisimulation from bisimulation up to. This is the previously proved fact. Fact is also a proof method which just takes facts and applies them, or kind of. So basically the idea is that what we want to prove here from this and this follows this. This is exactly what this fact, this already proved fact, means. So it just says, okay, this is already there by this already proved fact. Good, so now we have this union being a bisimulation relation. And then we can say, okay, then this union is in bisimilarity, because this is this key statement that any bisimulation relation is in bisimilarity. So we also prove it by just referring to the respective fact. But moreover, new keyword, I think, and again, it's kind of simulating the style that mathematicians would use. I shortly say what this means. Moreover, we have that k is included in this union, because for n equals 0, it's in there. And now this is some bit complicated, because I couldn't get it work with the automated provers, I think, because the automated provers were in a sense too powerful, and they tried searches that didn't lead to anything useful. So I thought I'd do things a bit more manually. I took this funpow0 lemma. So this is a lemma from the standard library, funpow0, and it says f to the power of 0 applied to x is x. So I want to, of course, to use it for this thing that f to expansion f to the power of 0 applied to k is just k, because I want to prove that k is included in this union. But now automated prover cannot find out that this is exactly the instantiation that it needs. So therefore, I give it explicitly. I don't say funpow, but I say funpow of this. We already had this capital letter of. This was application, basically, of implication. the small letter of this instantiation of schematic variables. So before we had here, what was it? We had these schematic variables, f and x, so something like universally quantified or arbitrary. And now we say of this and that. And now we have exactly this statement that we want, but actually not quite, because we also have this symmetric here. And this just means that we swap the sides. So we have this fact expression, this one, that just is this k equals this. The idea is that I substitute this k by that, and then apply this blast reasoner. But I cannot use just this unfolding, for example, that we had, I think, or the simplifier, because these will try to apply this equation that we have here as often as possible. But of course, then it would replace k by this, and then it would again pick the k and replace it by this, and so on and so forth, and would get stuck. And therefore, I have to use this really primitive method subs that does exactly one substitution, and without further parameters, or it just does it on the first k, basically. So I can actually show what it looks like after I have applied the subst. So I can say apply. This is a kind of imperative proving style, like in Cork, where you apply proof methods to change your goal state. So this is different from this nice structured proof cell with this proof in QED and by. So this is discouraged nowadays for good reasons. It leads to hard to read proofs, but you can use this imperative application of proof methods very nicely in order to find out what proof method to use. I mean, you don't come up with this thing here right out of the top of your head. So you can play with this, apply this proof method, and apply that proof method, and you found your way of how to use the different proof methods, then you just bundle this into this by clause and you're done. So for experimenting, this apply is very useful. For the finalized proof, you don't use it at all because it's ugly. So we have this goal here. So now this doesn't work. I will use this very nice word oops, which says say cancel the proof, and don't have proof anything. So we want to prove this here, and if you have this substitution, then we just get this. And this k is not touched, and this k is not touched. And the rest can then be sorted out with this blast, because the blast considers automatically some laws about this union and so on. And of course, if f to the power of 0 k, this is in this union because it's in this union for n being 0. Good. So what is this moreover? So this moreover is basically for accumulating facts. We say we have this, and we say moreover we have that. And we could say more moreovers. Didn't I already describe? I think I had this already at some point. And so we could have moreover blah, moreover that. And these facts are accumulated under the hood in some dedicated fact list, which is, I think, called calculation. And then we can say ultimately, and ultimately just takes this facts list calculation and makes it our facts here that this proof method here can use. So the then statement that we had here would always fetch the previously proved fact, and this ultimately fetches all the facts that have been listed after moreover and also before the first moreover. So every moreover gets the previous fact and puts it into this calculation list, and ultimately gets also the previous fact and puts it in the calculation set list, and then just takes this list. So we have this, moreover we have that, and then it's of course clear k is included in this union. This union is included by similarity. So k is included in by similarity, by transitivity of inclusion. I just say sim because I don't want to list the lemma name like from the standard library, like transitivity of inclusion, because this is so trivial. It's not worth listing it. And I should say by simplifier, the reader shouldn't care about how this works internally. Just look there and see, of course, that's something a human can figure out. And then we have established our theorem. You will see again, We use this prose style. What we get in the end is a logical statement with implications and schematic variables. So for any f and k, f is respectful, k is a bisimulation relation up to f, k is included in bisimilarity. And that's really the first really fundamental theorem, and it's quite an achievement. So we are here. It basically concludes bisimilarity. There are only a few technicalities that I will show next time. No, we are here. We know we can use up to methods, provided we have a function f that is respectful, but we have already established that certain functions are respectful. This was here. So, here. So constant bisimilarity is respectful, identity is respectful, respectfulness is preserved by function composition, by general union, and then also by binary union, and by dual. And we'll later see if we have transition systems where both the transition systems are the same, both the transition relations, then even by this chaining, by this lifted relation composition. And this way we can compose already a lot of respectful functions f that we can use for up to proofs. In particular, up to bisimilarity is possible. And later we will have also up to context. Good. Any questions? Okay. Anything interesting in the chat? Okay, Javi gave a comment. Yeah, this is the thesis. Okay, you can use question mark thesis instead of writing the whole expression to be proved. Yeah, that's the shortcut. Good, then see you all next week, hopefully. And then I will go to these remaining few bits of this up to context. And then I think we can look at weak bisimulation, weak transition systems and weak bisimilarity. And after that, we will go to up to context, which is maybe the most impressive part also. Good. See you all. Thanks for listening. Bye-bye.